Alright, so in this video I'm going to be explaining another important article with the title SSHPool, the separated subgraph based hierarchical pooling. So this paper in 2024. In this paper we developed a novel local graph pooling method, namely separated subgraph based hierarchical pooling for graph classification. We commence by assigning the nodes of a sampled graph into different clusters, resulting in a family of separated subgraphs. We individually employ the local graph convolution units as local structure to further compress each subgraph into a coarsened graph node, transforming the original graph into a coarsened graph. Since these subgraphs are separated by different clusters and the structural information cannot be propagated between them, the local convolution operation can significantly avoid the over-smoothing problem caused by message pathing through edges in most existing graph neural networks. By hierarchically performing the proposed procedures on the resulting coarsened graph, the proposed SSHPool can effectively extract the hierarchical global features of the original graph structure, encapsulating rich intrinsic structural characteristics. So, the aim of our work is to overcome the aforementioned shortcomings by proposing a new pooling method that focuses more on extracting local features from specific separated subgraphs. So this is a description of two pooling methods. Both the global and local pooling methods convert the original input graph into a global feature. On the left side, the global pooling tends to directly sum up or average the representations of all nodes over the whole graph structure. By contrast, on the right side, the local pooling tends to assign the nodes into different clusters and then hierarchically aggregate the nodes from the same cluster into a coarsened node, so resulting in a family of layer-wise coarsened graphs. So these group of nodes in this cluster are mapped into this supernode. Again, these groups are mapped into this supernode. These are mapped into this supernode. And so this is a coarsened graph, and now we have a global feature. So you know that you can represent GNN like this, that Z is the extracted graph embedding. And you can update the hidden embeddings. For example, diff pool is a kind of hierarchical pooling that I've explained in a different video, but the problem is that computationally expensive. It is, what else can we say? The good thing is that I don't know what to say, if it is a good or bad. Let's say good thing. The good thing is that we can fix the number of clusters in advance. But at the same time, the bad thing about this fixing the number of clusters in advance is that each distribution of a graph has each graph's data set has a different distribution. So you cannot always generalize in that fashion because you are superficially changing the topological nature of that graph. So this is the computational architecture of the proposed SSHPool. The first step is the assignment, where the input graph is decomposed into multiple separated subgraphs. Then the second one is the coarsening process, where these subgraphs are compressed into nodes of the coarsened graph. Let's have a reflection on this. It's like doing global pooling on local subgraphs. Global pooling of this, global pooling of another subgraph. Then you have a coarsened graph in this way. Then maybe another global pooling on this, then you can classify it. So this is the main motivation and idea of this paper. So the problem is the assignment and the local graph convolution. So we define the assignment ratio alpha, and unlike the classical hierarchical based diff pool, the proposed SSH pool is based on the hard assignment matrix. Each node cannot be assigned to multiple clusters. In fact, the hard assignment matrix can be computed through the soft one. Specifically, given the node embedding matrix, the soft assignment matrix is defined as this, and then you make it hard. Okay. And then we propose a local graph convolution unit to extract the local structural information. After several individual local graph convolution operations on the separate subgraph within the same graph, same layer of the proposed SSHPool, we aggregate the local information of different subgraphs to further generate a coarsened graph. So in order to match subgraph to the coarsened graph, we define a mapping vector S sub j to compress each subgraph into a coarsened node, where we split the hard assignment matrix into vector, and S sub j represents the nodes belonging to J's subgraph. So you get the idea. Then you can concatenate these representations of different supernodes, and that's it. You get X. Now, the global feature generation. The above definitions give the computational procedures of the proposed SSH pool for each layer. By hierarchically stacking the computational procedures with multiple layers, the initial graph, the proposed SSH pool can hierarchically extract the final global feature. Specifically, given the initial input graph associated with its node feature matrix and adjacent matrix, the whole process can be generalized as 9. So the attention is now can be calculated like this. The graph attention layer. After hierarchical pooling process, the original graph feature has been transformed into global feature in a hierarchical structure. Since there are multiple layer-wise stack local convolution unit sets associated with hierarchical substructures, resulting in possible degradation problems. To resolve this problem, we propose a graph attention layer to further integrate the initial graph embedding extracted from the global graph convolution and the global feature extracted from the proposed SSH pool. So we adopt the multi-layer perceptron as the classifier. So given this attention matrix that we have computed here, and a label set y, our GNN computes the predicted graph label. So probability is it encapsulates the probabilities whose amount is number of your labels. So we have a global convolution, then we give it to hierarchical pooling. This paper, the model is called SSHPool. And then we have graph attention layer. Finally, we give it to MLP for graph classification. So they compare it for different data sets for different models. For example, if you compare diffpool, which is very popular, with SSHPool for NCI1, you will see that from 62%, they could improve their model to 75, which is very good. Another one, let's say protein. Protein, from 74, they improved it to 79. Also, DND from 77 to 81. The biggest improvement is for, I think, this NCI1 and NCI 109, that we see a huge improvement. Other data sets, we don't see huge improvement, slight improvement. So the average rank is for their method.